Okay, let's do special relativity test 2020 ASC. Alrighty, question 1. Calculate the rest mass of a particle that has a relativistic momentum of that and a speed of 0.4 c relative to an observer on Earth. So obviously the question has something to do with relativistic momentum. They're telling us the relativistic momentum. The formula for the relativistic momentum is so relativistic momentum is the m0 v on root 1 take v squared on c squared. So that's your formula for relativistic momentum. 1 take v squared on c squared. Now, obviously, when the data sheet writes it down, they don't write m0, they just write down m. Okay? The reason why they do that is because basically the new school of thinking is that there isn't anything such as rest mass. So the new school of thinking is mass is constant. So if mass is constant, it just means calculate the mass. And if it's calculate the mass, the 0 is technically not relevant. So when it says calculate the rest mass of a cosmic particle, the old school way of thinking is that mass does dilate as velocity increases. The new school way of thinking is that it's not mass that dilates, it's momentum that dilates for a moving object. Mass is a constant property for any particle. So pretty much I got rid of the word rest, which allows me to get rid of that number 0, and then it allows me to write it the way the datasheet writes it. Honestly, that's just a technicality. It doesn't really make a big difference. Okay, so we have this, and we have to work out the rest mass, and they've given us the relativistic momentum. So the fact that they've given us relativistic momentum of that means that we have the value of this, and they've also told us a speed of 0.4 c relative to an observer on Earth, so we have the velocity. So pretty much, the velocity there and the velocity here. So pretty much all I need to do is solve for m. Honestly, the easiest thing to do is just rearrange for it. So if I rearrange for m is, bring the root to the other side. So p root 1 take v squared and c squared. Another way of writing v squared and c squared is v on c squared at the end of the day. So v on c squared all over v. Okay, so we just do some number plugging, sub in the momentum, so 3.08 times 10 to the negative 21 times root 1 take, the velocity is 0.4 c, so 0.4 c divided by c and then squared, all over the velocity, and this time I'm not going to write 0.4 c, I'm actually going to write down 0.4 times 3 times 10 to the 8. Alrighty, obviously in terms of cancelling out, the c and the c crosses out, so really what we're putting into our calculator is 3.08 times 10 to the negative 21 times root 1 take 0.4 squared all over 0.4 times 3 times 10 to the 8. So really that's what we're putting into our calculator. Be careful when you put it into there in terms of the number plugging, and then the mass that we get, or the rest mass that we get, up to you what you want to call it, is 2.35 times 10 to the negative 29 kilos. Okay, that is the mass of the particle, or you can say rest mass of the particle. All right, question 2, very, very, very common question. With reference to the equation for relativistic energy, explain why no object with mass can travel at the speed of light. And it says with reference to the equation for relativistic energy. Now, the equation for relativistic energy, also called total energy, is, so it's m0c squared, no, I'll just say mc squared because we're not going to write m0, so mc squared Lorentz. And what that really is mc squared all over root 1 take v squared on c squared. So that is a formula for total energy. Okay, again, you could write m0 if you wanted to. Okay, you could write m0 if you wanted to, or if you write it the way that the datasheet writes it, no m0. Alrighty, so with reference to this equation, explain why no object can travel at the speed of light. So if the velocity of a mass is equal to the speed of light. So if the velocity of any mass, of a particle with mass, if the velocity of a mass or a particle with mass equals c, if the velocity of a particle with mass equals c. And now I'm going to do some math. So if the velocity is equal to c, that means pretty much square both sides. Velocity squared equals c squared. All right, pretty much I'm going to be manipulating this to make it look like that. Okay, I'm going to be manipulating this to make it look like this. So v squared equals c squared, divide both sides by c squared. So that would mean v squared on c squared is 1. If v squared on c squared is 1, 1 take v squared on c squared is 0. And effectively that means square root of 1 take v squared on c squared is also 0. Which effectively means that this denominator is approaching 0. If the denominator is approaching 0, we all know that if the denominator of a fraction approaches 0, it means the fraction is approaching infinite. So what I have is mc squared on 1 take v squared on c squared is approaching infinite. Perfect. And that pretty much means total energy is infinite. All right, so effectively total energy is infinite. So we've just mathematically proven that therefore infinite energy is required. Infinite energy is required to accelerate a particle with mass to the speed of light. And one of the things that we'll do when we do cosmology is the fact that there's basically, the Big Bang Theory says there's finite amount of energy in the universe. So therefore, as there is a finite quantity of energy in the universe, it is impossible for an object with mass to reach the speed of light, or to be accelerated to the speed of light. To be accelerated to the speed of light. That's it. Simple as that. Alrighty, cool. Next one. A hungry astronaut is cooking noodles in his spacecraft. The spacecraft travels at 0.86 c relative to an observer on Earth. Alrighty, so that's the speed of the spacecraft. In the reference frame of the astronaut, the noodle takes 2 minutes to cook. Cool. Calculate the time taken for this event to happen in the reference frame of an Earth-based observer. So obviously an Earth-based observer is observing a very fast-moving spacecraft. And when we observe a fast-moving spacecraft, then all events in that fast-moving spacecraft, all events in that moving inertial reference frame, the events are dilated. So if the events are dilated, we feel it's going to take more than 2 minutes to cook. Remember, the astronaut is at rest with respect to the noodles. Since the astronaut is at rest with respect to the noodles, the astronaut will measure proper time of 2 minutes. So 2 minutes is the proper time. Since Earth-based observer is not at rest with respect to the noodles, the Earth-based observer will observe a dilated time. So the formula is T equals T0 Lorentz, which pretty much means T0 divide root 1 take v squared on c squared. Cool. And it's just number plugging now. So the proper time was 2 minutes. I'm keeping it in minutes because it says give your answer in minutes. So 2 minutes divide by root 1 take v. So the velocity was 0.86 c. So that's pretty much 0.86 squared c squared all over c squared. C squared crosses out. And that leaves us with 3.92 minutes. While the noodles are cooking, 2 minutes of time passes on the astronaut's clock. Fine. In her frame of reference, how much time passes on the Earth-based clock? Okay, so you have to be very careful. All right, be very careful with the formula that you wear, or with the concept involved. So I'll tell you what I mean about being very careful. Alrighty, because a lot of people are gonna write 3.92. All right, a lot of people are gonna write 3.92. Alrighty, now here's the thing. So obviously the astronaut will observe proper time, and since the astronaut observes proper time, the astronaut's clock showed 2 minutes of time passing. Alrighty. In her frame of reference, how much time passes on the Earth-based clock? Now here's the thing. The Earth thought that the ship was moving, or the astronaut was moving, the Maggie was moving. All of these are the same thing. Astronaut, Maggie, spacecraft, all the same thing. So Earth-based observers think this is moving. At the same time, the astronaut thinks that the Earth is moving. Alrighty, so what that means is the astronaut, even though she sees proper time, when she looks at her clock, she will see proper time. However, when the astronaut looks at the clock on Earth, because the astronaut thinks that the Earth is moving at a very high speed, the astronaut actually will see dilated time on Earth's clock. The astronaut will see dilated time on Earth's clock. So that's why a lot of people will get 3.92 minutes, because what they'll tell themselves is the proper time is 2 minutes. They'll also say that the velocity of the Earth with respect to them is 0.86 c, so then c squared crosses out, and then they'll get the same answer. But here's the thing you have to be really careful about. Yes, the astronaut will observe dilated time passing on an Earth-based clock. But what does dilated mean? Dilated means, in this case, we see dilated, and what dilated means is slow motion. All right, dilated means slow motion. So when basically the astronaut looks at the clock, instead of going, when she looks at her own clock, it goes tick, 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 tick. But when the astronaut looks at the Earth-based clock, it's going tick, tick, tick. All right, so time is passing very slow on it. Alrighty, which means that actually when 2 minutes pass on the astronaut's clock, then less than 2 minutes will be showing on Earth's clock. So even though Earth is dilated, and I know dilated sounds like a bigger number, but we will be seeing a smaller time value. That's why I say and that's so confusing, because I'm sure everyone would agree that 2 minutes is the proper time. 2 minutes is the proper time, so a lot of people would have subbed 2 into here, and then they would have got a 3.92 here. It is really important. I always do this for time dilation. Rather than telling myself what's proper time and what's dilated time, I find that it's much more suitable to remember that this is the big one and this is the smaller value. So big and small, as opposed to asking myself what's proper and what's dilated. I only do what's proper and what's dilated for things like length or momentum. For those two examples, I ask myself what's dilated or what's proper and what's not proper. Alrighty, like what's in terms of length is contracted. In terms of momentum's dilated. In those scenarios, I ask myself what's what's proper and what's not proper. For time dilation, I always ask myself what's the big number and what's the small number. Okay, so what I mean by that is, even over here, I told myself that t is the dilated time, so it's the big number. T0 should be the small number. That's how I think about it. So then I knew that obviously when Earth people see the astronaut cooking the space noodles, we knew that the Earth-based observer was going to measure a bigger time. So that's what I was solving for. Now, in this case, bringing it back to the question, when the astronaut looks at the clock on the Earth-based clock and she sees it moving in slow motion, I expect her to see a time less than 2 minutes. Okay, I expect her to see a time less than 2 minutes. So that means I'm looking for the smaller value. So in fact, I'm going to be subbing 2 minutes into here. And that is quite confusing, because 2 minutes technically is the proper time. But that's just what you have to do in order to be able to solve this question. So T0 on root 1 take 0.86 squared, c squared all over c squared. Obviously, c squared again crosses out. So really, we just have to bring that root to the other side. So t0 is 2 root 1 take 0.86 squared. Cool. That gives us a proper time of 1.02 minutes. Cool. Nice question. Alrighty. You have to remember time passes more slowly on the Earth-based clock. Okay. Now, you should have different answers for part A and B. Explain why there's a paradox. Okay. So obviously we have different answers, and the reason for the paradox, it all has to do at the end of the day with Einstein's theory of special relativity. So according to Einstein's theory of special relativity, according to Einstein's theory, the Earth observer basically states that time runs slower on the moving spaceship. The Earth observer states that time moves slower, that time runs slower, not moves, time runs slower on the moving spaceship. That's what the Earth-based observer. All right, paradoxically, that's why it's a paradox, because they're technically both correct, because they're both inertial reference frame. So paradoxically, the spaceship, I'll just say the astronaut. Paradoxically, the astronaut observer states that time runs slower on the moving Earth, because according to that, the Earth is moving, okay, on the moving Earth. Now, they're both correct because each of them thinks the other one's moving. That's why they're both correct. So therefore, both are correct in their own frame of reference. Both are correct in their own frame of reference. And that's why it's a paradox, okay? It's a paradox because they disagree, but at the same time, they both at least agree that each of the other objects is moving, and that's why they both are correct in their own frame of reference. Cool, nice question. Alrighty, now I see lots of objects, lots of velocities, so this makes me think this is like a relativistic velocity addition question type. The only thing confusing me a little bit is the fact that there's 4 objects: comet, alien canister, space cube, and Earth. So there's actually 4 objects. So I suspect, yeah, there's obviously 2 different parts. And remember, with questions like these, we only usually are meant to have 3 objects, okay? So anyway, space cube is traveling at 0.9 c towards a stationary observer on Earth. Alrighty. So that's what the space cube is doing. So 0.9 is with respect to Earth. I'm just going to write E next to it if it's with respect to Earth. So 0.9 c with respect to Earth. I won't actually write E. I'll just put a tick next to it if it's with respect to Earth. Okay. An alien canister is moving away from the space cube at a speed of 0.357 c. So this is moving away from the space cube at this speed. So I'm going to assume that this is with respect to the space cube, so it's not with respect to the Earth. Alrighty, fine. I've just put a little tick in there when it's with respect to the Earth, just to remind me what it is. Okay, tick doesn't mean that it's correct. Tick does not imply correct. Tick just, to me, means with respect to the Earth, so that I don't forget. Alrighty, so what do they want? They want the direction, speed, and direction of the alien canister in the Earth's frame of reference. Alright, so do you realize that it's got nothing to do with comet? Nothing to do with comet. Comet's irrelevant, so now we have 3 objects: alien canister, space cube, and Earth. What do we want the speed of? We want the speed of the alien canister in the frame of Earth's reference. Now, obviously, the Earth is stationary in this case, so we effectively want something without a dash. We want something without a dash. So in this case, I always write down what it stands for. U is the velocity of the alien canister with respect to Earth. Okay, because it's not got a dash next, because it says so. So then U dash, same letter, so it's the velocity of the same object, but it's with respect to the moving object. In this case, the moving object is the space cube. So it's the velocity of that according to the space cube. And then obviously V is a different letter. So V is the velocity of some other moving object or some other object, which is a spacecraft. But again, according to Earth, because there's no dash next to it. And obviously, we want U. And as per the data sheet, the formula for U on the data sheet is V plus U dash. Well, that part's Galilean relativity, but to make it Einsteinian relativity, we have to divide by 1 plus V U dash on C squared. That's it. Now let's just write down what they all are. What is the velocity of the alien canister according to Earth? It's going to the left, so I'm going to write down negative 0.357 C. U dash is the, and that's the one, this one, negative. We're trying to find out what this is. This one is question mark. The velocity of the alien canister according to the space cube is negative 0.357 C. And lucky last, what's the velocity of the space cube according to Earth? I've put a tick next to it as well. So that's with respect to Earth. It's 0.9 to the right, so positive 0.9 C. Great. I've got all the numbers, just got to plug it in. V is 0.9 C. U dash is negative 0.357 C. All over 1 plus 1 plus positive 0.9 C negative 0.357 C all over C squared. C squared just crosses out. So really what we have is at the end of the day we have 0.9, take 0.357 C all over, and this becomes one takeaway really, 0.9 times 0.357. Perfect. And that gives me a velocity of positive 0.8. So 0.800 C. So the fact that it's to the right, so you can say right or towards the Earth, whatever you want to say. So therefore, because in this case, if the velocity of the alien canister, according to calculate the speed and direction, so the velocity of this one, I know it appears left, but we got a positive number. So actually, the canister is moving at a speed of 0.357 C to the right, or sorry, 0.800 C to the right, according to Earth. Okay, to the right means towards Earth. So therefore, 0.800 C to the right, or you can write towards Earth. Okay, and that's our answer. A comet is approaching Earth at 0.75 C. Determine the speed and direction of the space cube relative to the comet. Okay, a comet is approaching Earth. Okay, so now everything to do with comet. Determine the speed and direction of the space cube. So now we ignore the alien canister. Okay, now we ignore the alien canister. This has got nothing to do with the alien canister. The new objects are comet, space cube, and Earth. And what do we want? We want the speed and direction of the space cube relative to the comet. Alrighty, the fact that we want something relative to the comet, this one was in Earth's frame of reference. So the Earth was stationary, so we wanted a U. This one now is relative to the comet. The comet is moving. So that's what tells me that what we want is a U dash. Since it's relative to the comet, we want a dash. Alrighty, so in this case, what does U dash stand for? U dash is the velocity of the space cube according to the comet. So U is the same object, velocity of the space cube. It's the velocity of the space cube, but relative to the Earth-based observer. And V, it's a different letter, so it's the velocity of the other moving object, which is the comet, according to Earth. Do we have the velocity? Yes. A comet is approaching the Earth at 0.75 C. So this is, again, with respect to the Earth. I put a little tick next to it. It's with respect to the Earth. Alrighty, and what do we have? What is the velocity of the spacecraft according to Earth? Velocity of the spacecraft according, or space cube, sorry, according to Earth is 0.9 c. This is the one that we're trying to figure out. And the velocity of the comet according to Earth is also to the right, so it's also positive, so 0.75 c. Both are positive because they're both to the right. And obviously we want to work out u dash. The formula for u dash, the Galilean formula for u dash is just u take v. Then to make that Einsteinian, we need to do on a 1 take uv on c squared. And now number plugging. It's very easy. Now that I've done that, it's really, really easy to do the number plugging. U is 0.9 c, v is 0.75 c. On 1 take, 0.9 c times 0.75 c all over c squared. C squared crosses out. So really what we're putting into our calculator is 0.9 take 0.75 all over 1 take 0.9 times 0.75. And that will give the answer in terms of c. And that gives us a velocity of plus 0.462. 0.462. You can say right, but it says relative to the comet. So right relative to the comet means away from the comet. Okay? Therefore, 0.462 c, you can say right or you can say away from comet. Cool. Nice question. Classic relativistic velocity question types. Alrighty. The distance between the Earth and the star Gliese is 14.84 light years in the reference frame of the Earth. The distance between the Earth and the star. Okay, so I'm just going to write down. So there's the Earth. There's the star, Gliese. And the distance between them, according to Earth. Now remember, the distance between them is space. Alrighty, alright. I always like to think of space as a piece of string. So the distance between Earth and Gliese, we'll assume center to center distance. Technically, the radiuses of this don't really matter because this is a very, very big distance. So this distance, aka this piece of string, is 14.84 light years long, according to Earth. Okay, and that 14.84 light years is obviously the proper length because obviously space is stationary with respect to Earth. Okay, and if Gliese is not moving, let's just assume this is not moving and this is not moving, then 14.84 light years is also the so that would mean that both Earth-based observers and Gliese-based observers would agree on a proper length of 14.84 light years if neither one of them is moving. So anyway, the space, or I like to think of space as a piece of string, is 14.84 light years long in the reference frame of Earth. In the future, a spaceship will travel at 0.79 c. Calculate the time in years required to travel between Earth and Gliese at this speed. Alright, well that's pretty easy. I'll just do s equals vt, to be honest. S equals vt. So t is s on v. The reason why I'm able to do that is because this t stands for the time with respect to Earth, s stands for the distance with respect to Earth, and then v is obviously the velocity with respect to Earth. So if everything is with respect to the same object, we're allowed to just do s equals vt. So the distance that it's going to travel is 14.84 light years, and the velocity at which it's going to travel is 0.79 c. Now I want everyone to know the definition of a light year. The definition of 1 light year is the distance that light travels in a year. So another way of saying the distance that the light travels in a year is the speed of light times by a year. So that's literally the definition of 1 light year, the speed of light times by a year. Because remember, light year is technically a distance, c is technically a speed, and 1 year is technically a time. Okay, so the definition of a light year is c times a year. So I'm just going to replace light year with c times a year, or c years. 14.84 times c times years, because that is what the definition according to this, 1 light year is this. So I've just replaced light year with c years. Okay, when I say c times by year, well, yeah, that's pretty much it. Okay, so c years effectively. And then all divide by 0.79c. And then what's so good about writing it the way that I have? What's so good about writing it the way that I have is that the c's cross out. Not just that, I actually get the answer in years, which is what they wanted, the time in years. So we didn't have to convert the years into like um, days, hours, minutes, and seconds. We didn't have to do that. So really, the answer is just 14.84 divided by 0.79. So the answer is 18.8 years. Calculate the distance between Earth and the star Gliese in the reference frame of the spaceship. So here's the thing. There's obviously a spaceship moving towards Gliese, right? So there's some spaceship moving towards Gliese. So now we think the spaceship is moving really, really fast. We think the spaceship is moving really, really fast. Space, or this piece of string, thinks the spaceship is moving really, really fast. But at the same time, the spaceship thinks Earth, Gliese, this space, or this string. It's much easier to think of it as string. So if the string thinks that the spacecraft is moving really, really fast, then the spacecraft thinks the string is moving really, really fast in the other direction. So the spacecraft thinks that this string will have a contracted length. So that's what the question is asking. What is the distance between the Earth and the star in the reference frame of the spaceship? So basically it's asking us to find out what the contracted length is. The formula for length contraction is L0 divided by Lorentz, which pretty much is L0 root 1 take v squared on c squared. For this one, I will ask myself what's contracted, what's proper. So obviously, the proper length is 14.84 light years. The spacecraft is measuring a contracted length. So L0, we can just keep everything in light years. We don't need to convert it into meters. So L0 is 14.84 light years on root 1 take 0.79 squared c squared all over c squared. C squared just cancels out. And then that gives us 9.10 light years according to someone on the spaceship. Okay, cool. Next question. All right, looks like a simultaneity question, the way that it's just the fact that we've got a train, we've got two people, it looks like a simultaneity question. So anyway, John is in the middle of a train. Television screens at the left and at the right illuminate simultaneously in his frame of reference. Okay, so that's the given statement. The given statement is that televisions at the left and right of the screen illuminate simultaneously in his being John. His being John. So they illuminate simultaneously in John's frame of reference. So the guy in the train thinks this and this one illuminate at the same time. Alrighty. So fine, and that's because the light is obviously, he's in the middle, right? He's in the middle. It says he's in the middle. Obviously, and his girlfriend Jamie is on the platform. She can also see the screens. So here's the thing. Obviously, if John thinks this light and this light illuminate at the same time, it means the lights are reaching him at the same time. And that's because John thinks that, well, because this distance equals this distance, so the distances are the same, the speed of light is the same. So then if the distance is the same, the speed is the same, then the time will also be the same. So the time taken to come here is the same as the time for the light taken to come here. So effectively, John believes that both TVs are illuminated, so they turn on simultaneously. They both travel equal distances at equal speeds to reach him, so then the lights will also reach him at the same time. So, explain the order that John sees the TVs switch on in his frame of reference. Alright, we just said so. Okay, so as both lights reach John simultaneously, and as both lights travel the same distance, So I'm being very, very technical. The distance that they both travel, John is obviously at rest with respect to the train. So John measures the proper length of the train. So as both lights reach John simultaneously, and as both lights travel the same distance, I'm going to write like proper length divided by 2 because they're in the middle. So if John observes proper length. So if John observes proper length, John observes this light to travel L0 on 2, and he observes this light to travel L0 on 2. So as both lights travel at the same speed, the same distance at the same speed, and in this case the same speed as the speed c, as both lights reach John simultaneously, and as both lights travel the same distance at the same speed, that would mean John sees the TVs switch on simultaneously. John sees, the only rational conclusion is that he sees the TVs switch on simultaneously. And that's what simultaneity is. Simultaneity is that if there is a spatial separation between the two or more events, if there's a spatial separation of two or more events, then different observers will in different reference frames will very likely disagree on the order of events. Okay, so John sees the TVs turn on simultaneously. Okay, so cool. So that's the first part. Explain the order that John sees the TVs. And also explain the order John predicts for Jamie in his frame of reference. Alrighty, so guys, obviously, Jamie thinks John is moving to the left. Jamie thinks John is moving to the left. That means that John thinks Jamie is moving to the right. So John sees the following things. John sees Jamie moving to the left. John sees Jamie moving to the left. Basically away from the left TV towards the right TV. So that's what John sees, Jamie moving to the left, away from the left one towards the right one. And remember, John thinks that both these TVs were illuminated simultaneously. So John thinks that, yep, this one and this one turned on at the same time, and Jamie's going to run towards this. So effectively, therefore, what John sees is that the light from the left TV, think about it, guys, John thinks Jamie's moving this way. So John thinks that Jamie a little bit later on is going to be like over here. That's what John thinks, that Jamie's going to be over here. So effectively, what that means is John thinks that this light has to chase Jamie, whereas the left light has to chase Jamie, whereas the right light pretty much runs into Jamie. So effectively, John believes that the right light has to travel a smaller distance and the left light has to travel a larger distance. So the light from the left TV basically chases Jamie, hence covering a larger distance, hence taking a longer time. At the same time, light from the right TV basically collides into Jamie. Alrighty, and if it collides into Jamie, hence covering a smaller distance. And if it's covering a smaller distance, hence taking a shorter time. So therefore, John sees that the light from the left TV reach Jamie before the light from the right TV. Other way around. Left TV, light from the right TV, because remember we agreed that the light TV takes a lesser time. So the light from the right TV reach Jamie before the light from the left TV. Okay, so that's what John predicts for Jamie. Basically, therefore, John predicts that Jamie sees the right light first. Okay, great. Explain how Jamie interprets the orders of the TVs switching on in her frame of reference. Now, there's two ways of doing it. All right, there are two ways of doing it. The easy way of doing it is when the light reaches John and when both lights reach John, those are two events that reach him at the same time at the same point in space. These are not at the same point in space. All right, this TV turning on and this TV turning on are events occurring at different points in space. So that's called spatial separation. However, the light reaching John and this light reaching John are two events that occur at the same time at the same point in space, meaning there is no spatial separation. And as there is no spatial separation of those events, all observers must agree in the order in which the events occur. Alrighty, so one answer that I could write down is this. Explain how Jamie interprets the order. You could say something along the lines of this, that as there is no spatial separation, as there is no spatial separation of as there is no spatial separation between what two events? There is no spatial separation of the lights from both TVs reaching John, as there is no spatial separation of lights from both TVs reaching John, as there's no spatial separation between those events. All observers must agree on the order of events. All observers must agree on the order of events. And we already agreed, the question already told you that John thinks that both lights illuminate simultaneously. Alrighty, so if both the lights illuminate simultaneously according to John, since there's no spatial separation, so as John sees both TVs illuminate, or both TVs turn on simultaneously, as he sees both TVs turn on simultaneously, switch on simultaneously, Jamie I'm not even, okay, so I'm answering, I just read the question, I'm not even answering the question. It says how Jamie interprets the orders of TV switching on in her frame of reference. Okay, so I thought the question is asking, explain how Jamie interprets the order of the TVs switching on according to John. I mean, whatever I've written is not wrong, it's just not answering the question. So as John sees both TVs turn on simultaneously, Jamie believes both both lights reach John simultaneously also. Alrighty, that is correct. It's just not the answer to it's not the question, okay? It's the answer to a question that it's not asking for, okay? But nonetheless, it's still correct. All right, I'll just do it in different color. So it is a correct statement. It's just not what the question is asking for. So what the question is asking for, explain how Jamie interprets the order of the TV switching on in her frame of reference. So here's the thing. We already said that John thinks the light from the right TV reaches Jamie before the light from the left TV. The way that Jamie interprets it is this. So here's the thing, guys. Remember, John thinks that the light from the right TV reaches Jamie before the light from the left TV. So how does Jamie interpret the fact that she sees the light from the right TV before the light from the left TV? So pretty much, because according to Jamie, this distance equal distances. Equal distances, or if I was being specific, this distance, equal distances. So how can Jamie possibly think that she sees the light from the right TV before the left TV? The distances are the same, the speeds are the same. The only rational conclusion is that this must have occurred at an earlier time. So let me actually answer the question, how Jamie interprets the orders the TV is switching on. So, as both lights travel the same distance, as both lights travel the same distance at the same speed, as both lights travel the same distance at the same speed towards her, towards Jamie, the right TV must have been turned on before the left TV. The right TV must have been turned on, must have been turned on before the left TV. And that is why the light from the right TV reaches Jamie before the left TV, according to Jamie. All right, this one's according to John. John thinks that yes, the light from the right TV will reach Jamie before the light from the left TV because of basically because of Jamie's relative motion. All right, if I was being a bit more specific, due to Jamie's motion. So John explains the event due to Jamie's motion, whereas Jamie explains it due to the order of events, due to the order of events. So for her, she doesn't think that she's moving. She just thinks, I wouldn't write the thing in red. The thing in red is just for you to understand. She also thinks that she sees the right TV turn on before the left TV, but purely due to the order of events. And what's so interesting is this. What's really, really interesting, obviously, if there's no spatial separation from both TVs, of the lights from both TVs reaching John, they both agree on the order of events. But here's what's so special. This is what's really, really special. So we agree Jamie thinks that John will see both lights at the same time. Now, Jamie thinks John is moving to the left. Jamie thinks John will be here soon. So here's the thing. Jamie thinks that this right light turns on first and chases John. So if I write that down, according to Jamie, again, it's not the answer, it's just adding to our knowledge of simultaneity. According to Jamie, remember, Jamie thinks the right light turns on first and then the left light turns on later on. Alrighty, and remember, she thinks John is moving to the left. So according to Jamie, John, the right TV turns on first, and first of all, according to Jamie, John is moving to the left. So here's one of the things. According to Jamie, John moves left. According to Jamie, the right TV turns on first and the light chases John. And the light chases John, tries to catch up to John. The left TV turns on second, and the light basically runs into John. The light collides into John, which therefore means that if this light chases John and this light runs into John and this light happened first, effectively we're agreeing that according to Jamie, therefore both lights reach John simultaneously. They both reach them simultaneously, and we already agreed with that. We already did agree with that. We did agree that according to, as there's no spatial separation, all observers must agree on the order of those events, and therefore Jamie believes that both lights reach John simultaneously. All right, both lights reach John simultaneously. So very, very nice simultaneity question. Extremely nice simultaneity question. Next part. Jamie sees a train moving at 0.91 c to a left. The train has a length of 240 meters. Jamie sees the train moving at that speed. Okay, so this is now some calculations. Jamie sees a train moving at that speed. The train has a length of 240 meters in Jamie's frame of reference. Now remember, Jamie observes a contracted length because Jamie thinks the train is moving. Fine. Calculate the time taken for the light to reach the right hand wall of the train. Okay, so the light to reach the right hand wall. So we want to know how long it takes for the light to go there according to Jamie. All right, very common question actually, extremely common question. So I want to know how long it takes for the light to go there. Now it's important for you guys to understand that yes, this light goes here, but at the same time, so that's the distance traveled by light. That is the distance that light will travel. Alrighty, it will go in all directions. There, in every single direction, into out of the page as well. So that light will travel there. But at the same time, the light doesn't just travel there. At the same time, the back of the train travels here. So that is the distance traveled by the train. And remember, the train was 240 meters according to Jamie. So since the train was 240 meters according to Jamie, and since the question wants the time taken for the light to reach the right-hand wall of the train according to Jamie, I don't need to do any length contraction formula. I just use the 240 meters. Pretty much what we're saying is that the distance traveled by the light plus the distance traveled by the train adds up to 240 meters. The distance traveled by the light is CT. The distance traveled by the train is VT equals 240. So CT, C is CT is CT, velocity of the train is 0.91, so 91 CT is 240. So what I have is 1 CT plus 0.91 CT, so 1.91 CT is 240. Therefore the time taken is 240 divide by 1.91 C. So what that really is 240 divided by 1.91 times by the speed of light. Cool. And that gives us a time equal to 4.19. 4.19 times 10 to the negative 7 seconds. Alrighty, that was an interesting question. Most of the times they would have actually told us the train's length in John's frame of reference. They usually would have told us the train's length in John's frame of reference. They would have told us, and remember, John was on the train, okay? John was on the train. So if they tell you the length of the train in John's frame of reference, and we want to know how long it takes according to Jamie, the first thing we would have had to have done is contracted the length of the train. Figured out what the contracted length of the train is according to Jamie. And then this wouldn't have been 240, this would have been whatever the contracted length of the train is. This was an interesting, easier version of the question because they actually told you the contracted length straight away. Alrighty, question 7. A high voltage in a particle accelerator accelerates protons from rest to a speed of 0.770 C. What voltage is required to do this? Okay, so a few concepts that we need to understand. So it's accelerating it from rest to that speed. So I want everyone to know that basically the energy change, the energy required to do this is a change in kinetic energy. And the formula for change in kinetic energy is not as simple as just half mv squared take, or half mv squared take u squared. That's using Galilean relativity. So in this case, I'm going to write it down like this. So the way I'm going to write it down is, first of all, I'm going to just write down the formula for total energy. The total energy, everyone should know, is basically rest energy plus kinetic energy. Rest energy is m0c squared. Kinetic energy is kinetic energy. In fact, kinetic energy is exactly what the the work done is. In this case, the voltage is increasing the kinetic energy. So in this case, because it starts off as stationary, the kinetic energy is simply Q, QV. Because we need to remember the formula that work equals work done, the definition of voltage is work done per unit charge. So if I rearrange that, work done is VQ. And in this case, the work done is a change in kinetic energy. And because it starts off as stationary, so I'm going to write down plus, that's kinetic energy. And because it starts off stationary, the kinetic energy is straight up just QV. Okay, the kinetic energy is straight up QV. Cool. Now that I know that, it's really, really easy. What does it want? Calculate the voltage required to achieve this. So effectively, if I rearrange for voltage, voltage is energy. Take m0c squared. It's n0c squared. Divide by Q. And the formula for total energy is m0c squared Lorentz. Now, you don't have to write the m0 if you don't want to. You can just write mc squared, but I'll write the 0 in this case. So m0c squared is your formula times Lorentz is your formula for energy. This is just m0c squared all over charge. Alrighty, nice question. So you just had to remember that physics, the electricity formula, that work done, or the voltage is work done per unit charge. Rearrange that, work done is VQ. And what that work does, that work is technically equal to the change in kinetic energy. And because it's at rest to begin with, the change in kinetic energy is equal to the kinetic energy. So I hope that makes sense. Voltage is work done over charge. So work done is this. That work achieves an acceleration, and because it starts off stationary, the change in kinetic energy is actually equal to the total kinetic energy. And that's what allowed me to replace EK with QV. Alrighty, and then really, if I was to simplify this, this is m0c squared Lorentz take 1 all over Q, which is m0c squared Lorentz is 1 on root 1 take v squared on c squared. Take 1 all over charge. Alrighty, and now what is it? It's a proton. So the rest mass of a proton according to data sheet, 1.67 times 10 to the negative 27. Speed of light, so that's 3 times 10 to the 8 squared times 1 over times 1 over root 1 take, what's the velocity? Velocity is 0.77, so 0.77 squared, c squared, all over c squared. Take 1, and then don't forget to divide by the charge. Divide by 1.6 times 10 to the negative 19. Cool. Just make sure you don't make any putting into calculator errors, number plugging errors, and you'll get a voltage of 5.33 times 10 to the 8 volts. Okay? Cool. Simple as that. What a very nice question. Okay, that's a very, very nice question, worth lots and lots of marks actually. So there you go, that is the voltage required to achieve that 5.33 times 10 to the 8 volts. Alrighty, calculate the de Broglie wavelength for a proton traveling at 0.5 C. Now this is, well, technically we need to do the waves topic for you to understand what de Broglie wavelength is. But the formula for de Broglie wavelength represents this has to do with the basically wave particle, wave, what's the word? So yeah, wave particle duality nature of light and matter. So when anyone mentions de Broglie wavelength, what they're basically talking about, a couple of things you need to remember. When they talk about de Broglie wavelength, they're talking about the wavelength of a particle, okay? They're talking about the wavelength of a particle or matter, okay? However you want to think of it. They're talking about the wavelength of a particle, okay? And the formula for de Broglie wavelength that we just need to know, the formula for the de Broglie wavelength of a particle is h on momentum, okay? And usually, h on momentum is h on mv. Usually that's the formula for momentum, mv. Unless you're talking about relativistic speeds, and we are talking about relativistic speeds, we're talking about 0.5 c. So in fact, the correct formula wouldn't be this. The correct formula would be h on, and then it would be the relativistic momentum. And the relativistic momentum is not just mv, it's mv on root 1 take v squared on c squared. So that's actually the correct formula to use if something's traveling at a very high speed. This formula does the job at low speeds, but then as soon as the speed starts to get close to speed of light, so 0.5 counts, we start to use that formula. So effectively, this is all we got to do. We just got to put everything into this equation. Okay, we just got to put everything into this equation. The de Broglie wavelength is that. Okay, h on that. If you want to play it safe, a safe way of doing it is just saying h on p and just work out the momentum first. Okay, so h is Planck's constant, 6.63 times 10 to the negative 34. And I'll just work out the relativistic momentum on the side. So the relativistic momentum is mv. All right, you can write 0 if you want to. Datasheet doesn't. So 1 take v squared on c squared. So what is the mass? Proton, so again 1.67 times 10 to the negative 27. Speed of traveling is 0.5 times by the speed of light. All over root 1 take v squared on c squared. 0.5 squared c squared on c squared. C squared just crosses out. So what we have is therefore 2.89 times 10 to the negative 19. If I did have to write units, kilograms, meters per second. That's the momentum. Now that I've got the momentum, I can just sub it into here. So we sub it in, 2.89 times 10 to the negative 19. Great. That gives us a de Broglie wavelength of 2.29 times 10 to the negative 15 meters. That demonstrates that even the proton has got a wavelength associated with it. All right, and that's what the wave-particle duality of light and matter basically says, that both light and matter is both a particle and a wave at the same time. So this is obviously, if it's a wave, this is the wavelength of that moving particle. All right, number 9. Calculate the total energy released when a neutron undergoes beta decay. So this has got something to do with a bit of year 11 physics as well as energy mass equivalence. Assume the mass of the anti-electron is this and the mass of the neutron is this. You may also assume that all the particles involved are at rest. All right, so what do we have to do? We have to calculate the total energy released. This is literally like a year 11 physics question. So first we have to work out the mass defect. The mass defect is the mass of all the products minus the mass of the reactants. Alrighty, so what are the products? The products are this, this, and that. So this is a proton, so 1.67 times 10 to the negative 27, followed by a beta negative particle. A beta negative particle is an electron, so that would be 9.11 times 10 to the negative 31, plus a antineutrino, and they've told us that the mass of an antineutrino is this, 1.25 times 10 to the negative 37, minus away the mass of the reactant. The reactant is a neutron. The neutron is, they've told us the mass of a neutron is 1.675. Cool, pretty easy. So these three were the masses of these three things, and then I've just minused away the mass of a neutron, which is this, which they told us. So the mass defect is equal to 4.09 times 10 to the negative 4.09 times 10 to the negative 30 kilos. That is the mass defect. Alrighty, great. And if that's the mass defect, therefore, we all know how to convert that into, and this is in kilos. Alrighty, so I hope you guys remember last year there were two formulas. One was E, so there was one was E was the mass defect times 931.5, or I think you just did 931. This works if you want the energy in mega electron volts and if the mass defect is in kilos. So that does the job. However, you otherwise use the formula E equals mc squared. This is if, oh sorry, I don't know why I said kilos. This is AMUs. And if the mass defect is in AMUs, we use this formula if you want the energy in joules and the mass is in kilos. So what does it want? It's given us all the masses in kilos, and therefore I'm going to be using E equals mc squared. Okay, that's your energy mass equivalence formula. So 4.09 times 10 to the negative 30 times speed of light squared. So that's 3 times 10 to the 8 squared. All right, if you're really good, you won't even bother writing 3 times 10 to the negative 8 squared on your on your calculator. You'll just write 9 times 10 to the 16. Alrighty, and that gives us an energy of 3.68 times 10 to the negative 13 joules. That is the energy released. Okay? Cool. Easy peasy. Alrighty. Last question. In the Large Hadron Collider, a proton travels to the right, collides with an antiproton traveling to the left. Both particles travel at the same speed. Great. When the two particles collide, they annihilate and release 2 photons. Okay, so the two collide. So they're both particles, now proton and antiprotons. The same mass, traveling at the same speed. All right, 2 things with the same mass, traveling at the same speed. They collide and they release 2 photons. Fine. Calculate the speed of each proton before the collision. So here's the thing. What energy turns into what energy? So I want everyone to realize that what we have is the energy of the proton times 2. They both have the exact same energy, same mass, same speed. And all of that is turned into 2 photons, equals to energy of photon times 2, because they each have this frequency. So then the times 2 just cancels out. So effectively what we have is energy of the proton equals energy of the photon. Now, what's the formula for energy of a proton? Well, when I say energy of a proton, I mean total energy. And the formula for total energy, we already agreed, is m0c squared Lorentz. You don't have to write the 0. Energy of the photon is hf. So effectively, I'm just going to solve for Lorentz first. Okay, I mean, lots of ways of doing it. You can solve for Lorentz first. You can solve for the velocity straight away. Completely up to you. If I write what's going to be the easiest way? The easiest way for me to do this is going to be letting Lorentz equals hf divided by m0c squared. I'll do that first. I think that'll be the easiest thing to do. So h is Planck's constant. Frequency is 5.2 times 10 to the 23. All over mc squared. So the mass of a proton, 1.67 times 10 to the negative 27. And then times that by speed of light squared. So 3 times 10 to the 8 squared. That will allow me to work out what Lorentz is. And remember, at the end of the day, what is the Lorentz? Lorentz is root 1 on root 1 take v squared on c squared. That's what Lorentz is at the end of the day. 1 on root 1 v squared on c squared. Alrighty. So, first thing first, I have to work out what this is. Okay, so effectively, what this will equal to is, alright, so I'll just do the calculation for that one. My marking key does it slightly differently, so I'll do the working out for that. If I do the working out for that, I'm getting, give me 30 seconds. Alright. I'm getting, basically, equals to, this value here is equal to 2.2938, 2.293815. That should be close enough. 2.293815. That is what the Lorentz factor is equal to. So now I just need to rearrange this for velocity. So if I rearrange this one for velocity, so we've agreed the Lorentz factor is this. Now let's just rearrange this for velocity. To rearrange this for velocity, so it's 1 divided by 2.293815 equals root 1 take, and then I'll rewrite this as v on c squared. So I hope you realize what I did. I brought this to the other side as a times, and I brought this to the other side as a divide. And then I square both sides. So this here really is pretty much what we have is 0.435955 equals root 1 take v on c squared. So then I want to get rid of the root. So then what I'll do is I'll just get rid of it right here and then just write down this squared equals that. Then bring the v on c squared to this side. Bring the 1 take 0.435955 to the other side. So v on c is equal to square root of that. Alrighty, square root of that, which is square root of 0. We'll just write square root of 1 take 0.43595, and I can actually bring the c to the other side at the same time. So v is just square root of that c. That's what it's equal to. Okay, perfect. And that gives you exactly 0.900 c. All right, if you want, you can change that. It says give it either as a proportion of c or use SI units. 0.9 times by the speed of light is basically 2.70 times 10 to the 8 meters per second. Either or. Alrighty, perfect. So just a lot of math, but you just have to realize that what's happened is the total energy of the proton, both the rest energy and the kinetic energy, has got turned into the energy of the photon. Okay? Calculate the magnitude of the momentum of each photon released. We want the momentum of each photon. So obviously, which formula do we have that's got momentum in it? Especially, and remember, you can't use this formula for momentum. So the most common formula that comes to mind when you think of momentum is the formula that comes to mind is momentum is pretty much mv, or if you're doing a relativistic momentum, momentum is mv on root 1 take v squared on c squared. Now we can't use either one of these formulas, and why not? Because the mass of a photon is 0, all right? A photon has a mass equal to 0. So which formula do we use? Now the only other formula that I know that's got momentum in it is the de Broglie wavelength formula. And the formula for de Broglie wavelength is h on p. That's the only other formula which has momentum in it. Rearrange this. Momentum is h on the de Broglie wavelength. And that, guys, is exactly the formula that we're going to use. We're just going to effectively use momentum. Now, it's technically not the de Broglie wavelength because the photon is not a particle. It's actually just a wave itself. So we just have to do momentum is h divided by that. Simple as that. So what do we know h is equal to? H is 6.63 times 10 to the negative 34. And do I have the wavelength? I have the frequency, so I can turn that into a wavelength. We should remember from last year that the formula is v equals lambda f. Yeah, the formula is v is lambda f. If you're specifically referring to the speed of light, c is lambda f. So rearrange this, that would mean that the wavelength is just c on f. Okay, so instead of writing this, we're going to write equals h on, I'll just work out the wavelength first on the side. Wavelength is c on f. C is 3 times 10 to the 8. Frequency is, they told us, 5.2 times 10 to the 23. So first, I'll work out the wavelength, and then I'll just do Planck's constant divide by that. So this one's 1.15. Sorry, wrong one. This one's 5.77 times 10 to the negative 16. We do this, divide 5.77 times 10 to the negative 16. Technically, it's like 7710. Use the exact answer. So 10, 5.7710 times 10 to the negative 16. And that gives us a momentum of 1.15 times 10 to the negative 18, and momentum is kilograms meters per second. So interesting formula. So we couldn't have used the other formulas for momentum because they both had mass. Couldn't have used this one, couldn't have used this one. They both had mass. In the end, the only other formula that didn't have mass is this. So it's important for you to note that when they're talking about momentum of a photon, we have to use the formula for de Broglie wavelength. All right, well done. That's the end of the special relativity test. Well done.